Welcome to the MOOCs course Transport Phenomena of Non-Newtonian Fluids. The title of today's lecture is Quasi-Steady Analysis of Simultaneous Heat Transfer, Mass Transfer and Chemical Reactions. So, in this lecture and then coming couple of lecture, we will be discussing problems where simultaneous heat and mass transfer, plus in addition to that there may be reactions also. Such situations, such problems we will be discussing, but we will be taking pseudo steady state or quasi steady analysis. What does it mean by? Till now, most of the problem, whether it is associated with the momentum transfer or heat transfer or the ongoing mass transfer, we have taken only steady state problems. Indeed, when we take the time dependent problems, then solution may become very difficult, and analytically doing or obtaining solutions is very difficult. We may need to move forward for the numerical solution under such conditions. But however, what we do, we take a in between step of steady and then completely time dependent, that is quasi steady or pseudo steady state problem we will be taking, where we will try to incorporate the time information as well, right. So, today we will be taking a case where simultaneous heat transfer, mass transfer and chemical reactions are occurring, and then under such conditions, if we wanted to apply the quasi steady models in order to get the solution. So, how to do, that is what we are going to see. For this purpose, we are taking a problem on combustion of carbon particle. We have a single carbon particle and then it is being combusted, right, and then it is producing carbon monoxide. So, 1 mole of carbon, half mole of oxygen reacting and then producing 1 mole of carbon monoxide, that is what situation we are taking. So, combustion of carbon occurs primarily through the following reaction at carbon surface. There may be other reactions also may be taking place. So, but we are restricting ourselves to one reaction that is given here, right. Now, consider a spherical carbon particle species C of radius r suspended in a gas mixture under pseudo steady conditions. The carbon particle that we are considering, we are taking spherical particle. In reality, it may not be necessary that carbon particle where the combustion going on may be spherical, it is not necessary, but for simplicity we are taking spherical particle. The particle radius is r, capital R. Obviously, this is changing with respect to time, because as time progresses the reaction progresses and then combustion of the particle takes place, and then obviously its size gradually decreases. So, this is a function of time, right, and then we are designating this species carbon as C, oxygen will be taking A and then carbon monoxide as B, okay. And this situation we are taking under pseudo steady conditions. Assume that gas contains only oxygen and carbon monoxide. Oxygen let us designate as species A, carbon monoxide as species B, okay. Then mole fractions xi infinity and temperature T infinity far away from particle are known. Infinity stands for infinite distance, far away. Infinite in the sense it will not be infinite, maybe compared to the radius of the particle, the far away conditions may be 100 times r or 200 times r, that is what in general taken as a kind of far away distance, okay. And then xi infinity in the sense xa infinity, xb infinity, xc infinity, that is ABC composition at far away distance are known. I stands for A, B or C, it can be anything. Reaction is very fast, that means moment the oxygen is coming and then reaching the carbon particle, immediately it is reacting and then forming carbon monoxide, that is what it means by fast reaction. One of the previous lectures also we have taken how to do the mass transfer analysis or how to consider the fast reaction contribution in the overall mass flux. Those problems we have taken both for heterogeneous and then homogeneous situations. So, there also we realize that if the fast reaction is very fast, so what happens, the concentration of the reacting species immediately falls to 0. That means x A at small r is equals to capital R is equals to 0, because this A is oxygen and then moment it reaches the carbon surface, immediately it reacts and then forms carbon monoxide, which is species B, right, and then particle is small enough that Peclet number is very smaller than 1 for both heat and mass transfer. So, what does it mean by if it is very small? So, two things we can understand from this one. So, whatever the transport is there, that is occurring because of the molecular mechanism only, right, conduction or diffusion depending on the transport, heat transfer or mass transport. Plus another thing we can understand is symmetry. Symmetry is there, so that whatever the concentration profile is there and temperature profile is there, they are function of r only, they are not function of theta and phi coordinates. This is what we can conclude from this assumption, and then if the Peclet number is very smaller than 1, then obviously these two are physically also more reliable. So, our problem has simplified. So, rather finding x as function of all 3 coordinates r, theta, phi, similarly temperature finding as function of all coordinates r, theta, phi, it has simplified by this assumption that the concentration and temperature are function of r only because of the symmetry, and then molecular mechanism is leading the transport process. So, that is the problem statement. So, first part of the question is that relate fluxes at the surface and then relate reaction rate to dr by dt. So, this r as function of time, this is what we know. So, rather directly relating the flux n to r, or relate the reaction rate, let us say Rs, if reaction rate is Rs, then relating it to r as function of time. What we have been asked? We have been asked to relate these fluxes to dr by dt, and then these reaction rates also to dr by dt. That is what we have to do, right. We do not want to relate to directly r function of time, but we have been asked to relate this flux and then reaction rate to dr by dt. So, what is the next part of the problem? Determine O2 flux at the surface, that is Na naught. Why at O2? Because the carbon particle is stationary, right. The bulk is having O2 and CO in general, right, because both of them are present at any time t, let us say at any time t. I am not saying that initially, at some time where the reaction has already progressed, because we have to relate all these quantities to time small t. Okay. So, when this O2 comes to the surface, then only reaction takes place, and then that reaction is very fast. So, at what rate this O2 is reaching, or what is the flux of this O2 at this surface, that is Na, okay, at r is equals to capital R, that we are calling Na naught. So, that Na naught, which is nothing but Na at r is equals to capital R, that we have to find out, because it will tell at what rate the O2 is reaching the carbon particle. So, then accordingly the combustion will also progress. Okay. Relate the heat flux and then reaction rate at the particle, that is the other question. Q and then R or Q naught, and then this Rs, let us say reaction rate is Rs, then these also we have to relate, we have to find out at the particle surface, that is at r is equals to capital R, we have to find out them. Then determine the particle temperature T naught. What is T naught? T naught is the temperature at r is equals to capital R, that is at the particle surface. This we have to find out, and then this is function of time actually, isn't it? Why? Because as the reaction progresses, the more combustion takes place and then temperature gradually changes. Okay. So, that also we have to find out. Okay. Now, schematically this is what we have a carbon particle whose radius is RT, and then gaseous stream or the surrounding of the carbon particle is occupied by the gas, which includes oxygen and carbon monoxide. Far away from particles, xi infinity and then T infinity are known, right. So, these are the things only known. nothing is known actually. Then just imagine, even if it is a steady state problem, if you know only far away conditions, you do not even know what are the conditions at the surface, neither in terms of concentration, neither in terms of flux, neither in terms of temperature, you do not know any condition at the surface. So, then even steady state problem you cannot solve this. In fact, because of that constraint of not having any condition, any information about the concentration or temperature at the surface, we have to, or we are forced to go for some kind of a pseudo steady approach or quasi steady analysis, right. So, now what I do, I will have a line, dotted line here, just outside of this circle, right, and then I am designating it as R plus, right, which is nothing but very first layer towards gas stream, right, and then inside this circle or inside this carbon particle I am drawing another circle, which is I am calling R minus, which is the very first layer towards the particle side. Basically this R plus, R minus are at the surface only, they are not different location, but for mathematical simplicity we are representing as one towards the particle and another face towards the gas side, because we have to do so many interfacial balances here. So, that this becomes very essential. Okay. So, that is the reason these two layers. Now, this is what we are going to have, we should have this picture in mind throughout the class of all the slides today, right. So, this is one, and then what happens, they are at interface, but finally after doing the balance we remove this R minus R plus, and then we have a superscript or subscript O indicating that is evaluated at the surface. Okay. This is the notations that we need to keep in mind until we complete the problem, right. Now, let A is O2 and B is CO and then C is carbon. This is given, Peclet number is very smaller than 1 for both heat and mass transfer. Because of that one, we can have a spherical symmetry, so that xi is function of both R and T only, but it is not function of theta and phi. Okay. Now, the first part of the question, relate fluxes at the surface and relate reaction rate to dr by dt. So, we will be developing some relations, let us say NAR, as NAR as function of dr by dt, then NBR as function of dr by dt, or Rs as function of dr by dt, these kind of relations that we are going to develop, that we can do only when we do the balances, right. So, in the interfacial species balance which follow a subscript O, so we are going to write, let us say the flux NAR at R is equals to capital R, we will be calling it NA naught. Similarly, NBR at R is equals to capital R, we will be calling it NB naught. This naught is following, indicating that interfacial species balance coming out because of the interfacial species balance. And it denote gas quantities evaluated at the surface, that is at R is equals to R plus, towards R is equals to R plus only gaseous species are there, because carbon is not going into the gaseous state because it is a solid, carbon is a solid particle, right. Then for the carbon, if you do the balance, then what you have towards the gaseous side minus towards the particle side should be equals to the rate of reaction, right. Towards the particle side or gaseous side, it is same, Nc minus Cc dr by dt at R plus minus Nc minus Cc dr by dt at R minus. They are not same but similar, mathematically similar, but quantity wise they are very different. Okay. And this difference has to be balanced by the rate of reaction, right. So, now here R plus is what? R plus is the location towards the gas side. Towards the gas side there is no carbon at all, it is only gaseous components are there, carbon is present only towards the particle side. So, Cc is 0 and then obviously Nc would also be 0, right. And then R minus, towards R minus, Cc is pure carbon, it is a pure carbon, towards the particle side it is pure carbon, because whatever the gases product they are forming including CO and then reactant O2, they are once the oxygen reaching the carbon particle surface, once the oxygen reaches the carbon surface then immediately the reaction takes place and then CO forms. That CO also goes into the bulk of the reaction, bulk of the let us say. So, moment this O2 comes here, immediately CO will form and then this will go and then diffuse to the bulk gaseous stream, right. So, that means what happens at R plus there is no carbon, only gaseous streams are there, and these CO etc. they are not coming into the carbon particle, that is what it means by they are not coming inside the particle, gaseous streams are not penetrating into the carbon particle, they are diffusing from the surface after reaction, they are through the mechanism diffusion they are going back into the bulk stream, bulk gaseous stream, right. Similarly, carbon particle is a stationary carbon particle whose size is decreasing because of the reaction, but carbon as a particle, as a solid, it is not going into the gaseous stream, right. So, these constraints we are going to apply for all three components, carbon, oxygen and then carbon monoxide when we do the balance. So, Cc is pure, so then inside the particle there is no flux, so then Nc is 0, and then Rsc is that rate of reaction with respect to carbon, C stands for carbon, right. So, at R plus carbon is non-volatile, so Nc is 0 and then Cc is also 0 because towards gas there is no carbon at all. So, obviously Cc would also be 0. At R minus stationary and pure carbon is there, so Nc is 0, Cc would be there. So, then what we get, dr by dt is equals to Rsc divided by Cc, or Cc dr by dt is equals to Rsc divided by Cc. Rate of reaction of that component with respect to C, rate of reaction with respect to C divided by the concentration of C, that is carbon. So, this is one equation, that dr by dt we related to rate of reaction. Okay. Then similarly, if you do the oxygen balance, A stands for oxygen. So, Na minus Ca dr by dt at R plus, that is towards gaseous stream, minus Na minus Ca dr by dt at R minus, that is towards the particle side, should be balanced by the Rsa, that rate of reaction with respect to A. So, this R plus is the location of towards the gas side. Towards the gas side at the surface, this is at the interface, right, particle surface. At the interface, Na is there, the oxygen is reaching the surface, and then only the reaction, combustion reaction is taking place between carbon and an oxygen. So, it should be there. So, at the surface we have already designated that quantities are provided with naught, Na, so Na naught, Nb, so Nb naught, like that. But this Ca, what should be Ca? The concentration of oxygen, it is coming with certain concentration and then reaching the particle surface, but moment it reaches the particle surface, immediately it is reacting and then carbon monoxide is forming. We are assuming that the 100% oxygen is being consumed for the combustion with the carbon particle. So, then its concentration is 0, at the surface it is 0. And then R minus is towards the particle size. Towards the particle size there is no gas diffusing into, the gas is not penetrating inside the particle. gases are coming, oxygen is coming and reacting on the surface, and then carbon monoxide is forming. That carbon monoxide is also diffusing back to the bulk gases stream, but it is not penetrating into the carbon particle. So, both Na and then Ca would be 0. That means Na is equals to Rsa, that Na at R is equals to R we are calling Na naught. So, Na naught is equals to Rsa. So, flux we related to the rate of reaction. Now, similarly, if you do for carbon monoxide, B stands for carbon monoxide. So, Nb minus Cb dr by dt at R plus, that is towards the gaseous stream, minus Nb minus Cb dr by dt at R minus, that is towards the particle side, should be balanced by the rate of reaction with respect to the carbon monoxide B. Right. So, now here at R plus, moment the oxygen is coming and then reacting with the carbon particle, immediately on the surface carbon monoxide is forming, that is diffusing back into the bulk gaseous stream. So, obviously it would be there, flux of carbon monoxide would be there, something we do not know, we will find it. So, that we are calling Nb naught, because any quantity, whether it is concentration or flux or whatever, if it is at the interface, we are designating, we are using subscript naught. Okay. And then this Cb is nothing but the concentration of carbon monoxide towards the gas side. It is towards the gas side. So, definitely moment of definitely when a carbon particle is reacting with the oxygen particle, carbon monoxide is forming. So, definitely it is there. How much it is we may not be knowing, but it will be there. So, both these terms would be there here in this case of CO, but R minus case, that is towards the particle size, to the interior of the particle, gases are not being diffused or penetrated. So, their flux, their concentration would be 0. So, what we have, Nb naught minus Cb naught dr by dt is equals to Rsb. Fine. So, here the flux and then rate of reaction both are related to dr by dt. First case, only rate of reaction was related to dr by dt in the case of carbon particle. In the case of oxygen, only flux Na naught was related to the rate of reaction, right. In the case of carbon monoxide, both flux and then rate of reaction are related to dr by dt, right. Now, we look at the stoichiometry. So, 1 mole of solid carbon particle is reacting with half mole of oxygen gas to produce 1 mole of gaseous carbon monoxide, right. Then reaction stoichiometry, overall reaction rate, if it is R, it should be written like approximately Rsi by xi. I stands for any component A, B, C here, that is oxygen, carbon monoxide or carbon anything. Xi is nothing but stoichiometric coefficient here of the reaction. So, with respect to A is for the oxygen, it should be -1. With respect to B, product, B is carbon monoxide, so it should be +1, and with respect to carbon, reactant, so it should be -1 from this reaction coordinate, this one we are getting. So, that means we can write Rs is equals to Rsa divided by -of is equals to Rsb divided by +1 is equals to Rsc divided by -1. The +1 plus minus symbols we are using, indicating if it is a product then plus, it is a reactant then it should be minus. Okay. So, that is Rs is equals to -2 Rsa is equals to Rsb is equals to minus Rsc. So, this equation number 1, 2, 3, 4, these 4 equations we are going to use extensively in remaining part of the lecture. So, we should remember them or we should write them wherever we need them. Okay. So, next step is that combining interfacial balances and stoichiometric information. So, first balance, that is in the case of carbon particle, when we did, what we got? We got dr by dt is equals to Rsc by Cc, and then from this equation number 4, Rsc is nothing but minus Rs, right. that means dr by dt is equals to minus Rs by Cc. So, now this dr by dt and flux we are relating to the rate of reaction with respect to the overall reaction Rs, rather writing individually with respect to the A, B or C. Okay. Then second balance, in the case of oxygen, what we got, Na naught is equals to Rsa we got. Now, but equation number 4, according to equation number 4 from that is stoichiometric information that we had. So, Rsa is nothing but minus Rs by 2. So, Na naught is equals to minus Rs by 2. Then third equation, that is when we do the balance for carbon monoxide, we get Nb naught minus Cb naught dr by dt is equals to Rsb, and this Rsb is nothing but Rs from equation number 4. So, Rs, and then this minus Cb naught dr by dt I bring it to the right hand side, so that I can have plus Cb naught dr by dt, right. So, now Rs plus Cb naught dr by dt is nothing but minus Rsc by Cc, that is what we get just now. So, now from these two terms Rs, if I take common, 1 minus Cb naught by Cc. Now, at the surface Cb naught concentration is going to be very much less compared to Cc, because moment it forms after reaction between C and O2 immediately diffuses back to the bulk of the stream. But the carbon is there only, whatever its concentration is there, its size may be reducing, particle size may be reducing with respect to time, but the concentration wise it is going to be there only, whatever the initial concentration maximum is there, pure carbon, that would be there till the last drop of that carbon particle is reacting. So, compared to Cc, Cb naught is going to be very small. So, then this ratio is going to be close to 0. So, then Rs 1 minus Cb naught by Cc, we can write Rs multiplied by 1, and then this Rs is nothing but, from this equation we have Rs is nothing but minus 2 A naught, that is Nb naught is equals to minus 2 Na naught, that is what we had. Okay. So, finally, dr by dt is equals to minus Rs by Cc and Nb naught is equals to minus 2 Na naught. So, in addition to first 4 equations, this fifth equation is also going to be very essential for our remaining lectures. We do not need to remember any other equations, they will be derived subsequently one after other because of the mathematical simplification, but in coming all rest of the mathematical simplification, one or other of these 1 to 5 equations would be used. Okay. So, now the second part, that is O2 flux at the surface, that is Na naught. Actually, NaR at R is equals to capital R, we are finding that we are calling Na naught, because it is at the surface, at the interfacial locations, whatever the quantities are there, they are replaced by they are represented by subscript O as well. So, species conservation in gas, that is you have a particle and then surrounding gas also you are taking the spherical geometry like this. So, then in spherical coordinates, species conservation equation for the gaseous region if you do, which is in the spherical coordinates, you have dou Ci by dou T is equals to minus del dot Ni plus Rsi, right. In the gas there is no reaction taking place, in the gas stream there is no reaction is taking place, whatever the reaction is taking place, that is taking place right at the carbon particle surface, and then product carbon monoxide is diffusing back to the bulk stream of a gas, right. So, this is 0, and then also we take this dou Ci by dou T also 0 for the time being, we are going to consider that way anyway. So, then what we get, this is having Ni, Ni would be having NIR, Ni theta, Ni phi components, right. But problem statement is given that Peclet number is very less than 1. So, Ni theta, Ni phi are negligible. So, we do not need to write. So, but NIR terms should be there. So, that when you expand this one in spherical coordinates, after removing the dou ni by dou theta terms or dou ni by dou phi terms, this is the only term we are going to have. Okay. This is coming by expansion of this one and then striking of ni theta, ni phi terms. After simplification, this is what we are having, that is equals to 0. Now, r square NIR is equals to some constant with respect to r, but that constant is function of time, that is what we are taking, right. So, this constant whatever is there, that is constant with respect to r, because with respect to r we are integrating, but it is function of time only. So, that is what we are bringing in, that is how we are bringing in the effect of time here in the quasi-steady analysis. What is this ft and all that we are going to find out in the subsequent steps, right. Further, we understood just previous slide, equation number 5, NB naught is equals to minus 2 NA naught. So, obviously, NBR should be equals to minus 2 NAR for all R, that is for all R. We have done at the interface, but that is going to be true for all R values because of this speculate number very small, right. So, NBR should also be written as minus 2 NAR in compared to the, which is consistent with the NB naught is equals to minus 2 NA naught. Okay. So, we know that combined flux NAR is equals to minus C dAB dXA by dr plus XA NAR plus NBR. In place of NBR, we write minus 2 NAR, then what we do, we write NAR terms one side and then remaining terms other side. So, then we have NAR is equals to minus C dAB divided by 1 plus XA dXA by dr. Now, we want this NAR at R is equals to capital R, that is NA naught we want. That we can do only when we know what is this right side function of XA, because here also we do not know what is XA and then how it is changing with R. So, if we stop here, it is an incomplete equation, it is not usable, right. So, what is this XA as function of R, that also we have to find. Now, we simplify equation number 6 for XA. So, equation number 6 is this one in the previous slide that we have derived. So, dXA by dr we are writing one side, other terms we are writing the other side. So, now if you wanted to find out this XA as function of R, what is this NAR as function of R, that we should know. Indeed, that we already know that R square NAR is function of time, but what is this function of time we do not know. Maybe there may be R square terms, R terms may be there. So, we cannot directly write this one as ft and then integrate it, right. For that, what we try to do, we try to get over any such kind of things are there. So, then we try to get over of them. How we can do? We just now had R square NAR is equals to ft, right. So, this one if you write R square NAR is equals to constant, from this equation d by dr of R square NAR is equals to 0, which we derived previous slide. Okay. So, now this R square NAR is equals to C1, the C1 and the same in place of writing ft I am writing C1, so that I can write NAR is equals to C1 by R square, right. Now, at R is equals to capital R, NAR is nothing but NA naught, that is the designation notation that we are following, that should be C1 by capital R square, right. That means, C1 is equals to NA naught capital R square. That means, this C1 if I use here in this equation, I get NAR is equals to NA naught capital R square by small r square, right. So, work done. So, now this NAR you can substitute here and then you can do the integration to get XA as function of R, right. So, in place of NAR we can write NA naught capital R square by small r square, remaining terms are as it is. Then we then we take this dxa by 1 plus xa one side and other terms are other side. So, that by integrating left hand side we have ln 1 plus xa limits xa is equals to 0 to xa is equals to xa infinity. Xa is equals to 0, that means at r is equals to capital R. As already mentioned, at r is equals to capital R, when the oxygen comes and then reaches the particle surface, immediately it reacts with the carbon and then reaction nature is very fast. So, that at any time t, its concentration would be 0, because immediately it is reacting with the carbon and then carbon monoxide is forming. So, right at the surface, its reaction at any time we can take it as a 0. So, that is xa is equals to 0 at r is equals to r, and then xa is equals to xa infinity at r is equals to infinity, right, is equals to minus capital R square Na naught by C dAB, integration of dr by r square is minus 1 by r, limits r to infinity. So, it should be plus 1 by r after substituting the limits, and then left hand side we should be having ln 1 plus xa infinity, right side will be having minus r square Na naught by C dAB multiplied by 1 by r. So, square of the r and then that r will be cancelled out. So, then we have only minus r Na naught by C dAB, right. So, now here what we get, Na naught is equals to minus C dAB by r ln 1 plus xa infinity. So, this equation is in final form and then usable form, because C would be known for a given system, dAB would be known for a given system a priori, and then radius of the particle is known, initial particle, right. So, ln 1 plus xa infinity are known, they are given. Even this r as function of t also we know, alright. So, this equation is the final equation for Na naught. Now, once Na naught is known, Nb naught, dr by dt etc. can be easily found, right. How? We have already found that Nb naught is equals to minus 2 Na naught, that is equation number 5. Okay. So, Na naught just now we found it as minus C dAB by r ln 1 plus xa infinity. So, this you multiply by minus 2. So, that you will be getting plus 2 C dAB by r ln 1 plus xa infinity as Nb naught. And then Rs also we know. What is Rs? Rs is simply Nb naught, or Rs is minus 2 Na naught, which is same as equation number 8. So, equation number 8 and then 9 are same. One is indicating Nb naught, another indicating Rs, but both of them are equal to each other for this problem, right. And then dr by dt we found minus Rs by Cc from equation number 5, right. So, that we have already derived. So, here Rs is nothing but minus 2 Na naught from this equation, that is 2 C dAB by r ln 1 plus xa infinity and divided by Cc is there and then this minus is there, right. So, that is dr by dt. So, we got all the quantities, indeed flux, rate of reaction, dr by dt, all of them are interrelated now. Okay. So, we can find out if we know the size of the particle and then for stream conditions, then we can find out whatever we want. So, second part of the problem also completed. Now, third part of the problem, relate the heat flux and then reaction rate at the particle, that is again at the interface. So, interfacial energy balance, if you do, we are not taking any radiation, which may be possible in general in such kind of combustion problem, but we are not taking. So, the balance equation we do Er minus sigma Ci Hi bar dr by dt at r plus, that is towards the gas stream side, is equals to Er minus sigma I Ci Hi bar dr by dt at r minus, that is towards the particle side. Now, you may be asking why you are writing Er, why not just E? Because like in a Cartesian coordinate we have solved one problem, in this derivation also we have done. So, this E is having components Ex, Ey, Ez. Likewise, in this problem also in spherical coordinates Er, E theta, E phi are there. but in theta and then phi direction no heat transfer is taking place according to this condition given. So, we have only ER component. So, that is the reason only ER we are writing, right. And then this again includes the contribution of conduction, convection, work done due to the pressure, and then viscous stress or viscous dissipation terms, etc. All other terms are included here except the reaction or then mass flux part. So, those how to bring those mass flux parts in this ER or EX we have seen previously in one of the problems. Similar way that we are going to write for this case also. So, ER is nothing but Q naught, that is conduction part, because in this problem only conduction is taking place according to the problem statement and then conditions given in the problem statement, and then heat associated with the mass transfer part is nothing but this part, that is Na naught Ha bar plus Nb naught Hb bar plus Nc naught Hc bar minus Ca naught Ha naught Ha bar plus Cb naught Hb bar plus Cc naught Hc bar dr by dt. This is because of the reaction part and then change of particle size. That should be balanced by similar things would also be there for ER in the particle size R minus, that is towards the particles, right. But towards the particle the penetration of a species are not taking place, gaseous species are not penetrating into the interior of the particle. Moment they come, oxygen is coming, immediately reacting, carbon monoxide is forming, and immediately it is diffusing back to the bulk gaseous stream. So, no gaseous stream are going inside the particle, and then no heat conduction is taking place inside the particle. Whatever the heat transfer is taking place from the surface to the bulk of the gas stream only taking place. So, all the terms are negligible, right. So, this Q naught and then Na naught, Nb naught, Nc naught, all those terms are negligible towards the particle size. Only thing is there, that is Cc Hc bar dr by dt. Cc is the concentration of the carbon particle, Hc bar is that molar enthalpy of that carbon particle, and then dr by dt is that change in the size of the particle with respect to the time because of the reaction. So, now we simplify this equation. So, Q naught would be there towards the gaseous side, Na naught there is something, just now we derived an expression, Nb naught is also there, just now we derived an expression, but towards the gaseous stream the carbon is not there. Carbon is there only in the interior of the particle, from the surface to the interior, only that part only carbon is there. From the surface it is reacting and forming carbon monoxide. So, gaseous stream no carbon is there, so then this term is 0, right. Now, coming to this part, what we have Ca naught. Ca naught is what? Is a concentration of oxygen at the surface, right, at the surface, though it is towards the gas, but whatever the oxygen is there, that is immediately being consumed by the carbon for the combustion reaction. So, this is not there. Cb naught would be there because immediately after a reaction between carbon and oxygen, carbon monoxide is forming. So, it must be having some concentration that is designated by B. So, Cb naught would be there. Then again Cc naught is nothing but the concentration of carbon towards the gaseous side, it is not there. Towards the gas side it is not there, because it is there only towards the particle size. Towards the gaseous side only oxygen and carbon monoxide are there. So, then what we are having, Q naught Na naught Ha bar plus Nb naught Hb bar minus Cb naught Hb bar dr by dt is equals to minus Cc Hc dr by dt, right. So, the same equation is written here once again, right, but whatever Na naught was nothing but minus Rs by 2 from equation number 5, and then Nb naught is nothing but simply Rs, and then this dr by dt is nothing but minus Rs by Cc from equation number 5. So, that we have written. So, same thing in the right hand side also, in place of dr by dt minus Rs by Cc we have written. Okay. Refer equations 4 and 5 for this transformation in terms of Rs. Okay. So, Q naught, what we are doing, we are combining this term and then this term and this term, and then writing Rs multiplied by minus HA bar by 2 plus HB bar minus HC bar multiplied by Rs, because here this CC is already cancelled out, and then this remaining term is nothing but plus CB naught HB bar Rs by Cc is equals to 0, and now this is nothing but delta HR for the entire reaction. A, enthalpy associated with the reactants, and then C is also associated with the reactants, and then B is associated with the product enthalpy. So, this is for the overall reaction. So, that is Q naught plus Rs delta HR plus CB naught HB bar by Cc Rs is equals to 0. So, now this equation you have to solve to get this Q naught, because the part of the question is that one only. We have to find out heat flux at the particle surface, that is Q naught. So, this equation, if you can solve, you can get this Q naught, but that is not possible unless and until you know some kind of information between these two. So, what we assume that this delta HR is much higher compared to the CB naught HB bar by Cc, or CB naught HB bar by Cc is very smaller than the delta HR, and then use Fourier's law of conduction for Q naught. Then you can solve this equation, because in general delta HR of the reaction you can know, they are provided or from the thermodynamics or reaction kinetics of non-isothermal reactions you can find out. So, that should not be a deal. Okay. And then this should also be making sense, because compared to the concentration of the carbon, concentration of carbon monoxide is very small at the interface. So, this ratio is going to be very small, close to 0, as we already seen. So, the overall when it is multiplied by HB bar, it is going to be very small compared to the heat of the reaction, that is delta HR. Okay. So, Q naught we can write minus Kg dt by dr at R plus is equals to minus R delta HR. So, now this equation you can solve, right. Only thing that you need to know what is dt by dr and all that. G we are writing just to indicate that is towards the gaseous side, whatever the conduction is there towards the gaseous side, otherwise we may be confusing with K of a carbon particle. Okay. This is all we are doing towards the gaseous side. So, that was the part 3, that is finding the heat flux at the surface. Okay. If you know the heat of the reaction and then Rs, Cc, you can find out that particular Q naught at the surface. Okay. Now, determining the particle temperature T naught we have to find out. Particle temperature at the surface whatever is there, that we are designating as T naught. So, what we do now for this purpose, we will be writing energy conservation in the gas. So, what we got, dou by dou R of R square ER is equals to 0, that we already got, which is pseudo steady spherically symmetric case. So, this we got it as R square ER is equals to F of T. Okay. Constant, that constant is function of time, it is independent of R, but function of time. So, we can write ER is equals to Ft by R, and then ER is having the conduction part, and then mass transfer part is equals to Ft by R square. So, here NCR is anyway 0, NAR is nothing but we got Na naught capital R square by small r square, HA bar is as it is, NBR is nothing but minus 2 NAR. So, minus 2 NAR is again Na naught capital R square by small r square, HB bar is equals to Ft by R square. Q naught is simply minus Kg dou T by dou R. Okay. So, this equation further we can write by taking Na naught capital R square by small r square as common. So, the remaining terms are these two. right. This equation what we do? We divide both sides by minus kg. That dividing we will do later. The same equation is given here now. Now, what we do? We have to take some reference temperature in order to define these things. These HA bar, HB bar usually defined with respect to some reference temperature. So, that we can write, we can bring in CPA bar, CPB bar, delta T, etc., because CPA, CPB information are known for many of the cases in general, okay, from the standard thermodynamic books. So, assume that HI bar is nothing but HI bar star plus CPI bar delta T is nothing but T minus T star is some reference temperature, let us assume. So, that this equation we can write minus Kg dou T by dou R plus Na naught capital R square by small r square multiplied by HA bar minus 2 HB bar with stars plus CPA bar minus 2 CPB bar multiplied by delta T, that is T minus T star. This delta T is only for this CPA bar minus 2 CPB bar is equals to Ft by R square is as it is. So, now this equation what we are doing, divide by minus Kg both sides to get this equation. So, that is dou T by dou R minus Na naught capital R square by Kg small r square CPA bar minus 2 CPB bar T minus T star is equals to Gt capital R by small r square we are writing, right. So, this whatever term is there, this term is combined together and written as like this. So, Gt capital R by small r square is nothing but Ft by R square Kg plus Na naught R square by Kg R square Ha bar star minus 2 Hb bar star, right. Okay. So, now these Ft functions they are not mixed with R square, they are written, but they are not combined, they are separately there. So, we can integrate them later anyway. So, finally, this is the same equation we have written here. Now, let that reference temperature T star is equals to T naught. So, that this equation we can solve. Further, what we are doing, that T minus T naught we are taking as capital theta, right, in order to do the non-dimensionalization, and then small r by capital R we are taking eta, and then whatever this constant Na naught capital R by Kg CPA bar minus 2 CPB bar is there, that we are calling lambda, capital lambda. So, that this equation number 12 will become dou theta by capital R dou eta minus delta capital R theta would be there, this only here, this this entire thing except the small r square, whatever the terms are there, this entire thing is nothing but capital lambda except this r square. We are in the lambda we are not having this square term. So, that is the reason this r is coming here, and then small r square is nothing but eta square capital R square, delta T is nothing but capital theta is equals to Gt capital R by small r is nothing but capital R eta. So, squares. So, that dou theta by dou eta minus lambda theta by eta square is equals to zeta by is equals to G of T by eta square. So, at eta is equals to 1, theta is equals to 0. To find out T naught, we must evaluate theta as function of location r is equals to infinity and time, that is T infinity minus T naught, because T infinity is known, right. So, this equation if you solve in at r is equals to infinity, you can find out what is this T naught. So, that we are going to do. So, the equation is written here once again, and it is in the form dy by dx plus py is equals to q, p and q are functions of x. So, its solution is that y multiplied by integration factor is equals to integral of q if dx, where if is nothing but exponential of integral p dx. So, here p is nothing but minus lambda by eta square, and then q is equals to zeta by g, and then q is equals to g by eta square. Hence, integration factor would be exponential of integral minus lambda by eta square d eta is equals to exponential of capital lambda by eta, and then solution would be theta multiplied by this if is exponential of capital lambda by eta is equals to integral g function of t by eta square multiplied by if integration with respect to d eta plus integration constant, which is again function of time. Now, we got another integration constant, which is function of time, which is constant with respect to r. So, that equation further if you solve right hand side integration, so then you have this equation. So, that exponential of capital lambda by eta if you take to the right hand side. So, this theta is nothing but this one, right. So, next part what we are doing? We are writing ht multiplied by exponential of minus lambda by eta minus gt by lambda, because this and this exponential of one is plus, another one is minus. So, then exponential of 0 is 1. So, this is the temperature distribution as function of r and t, but it is written in dimensionless form. But this equation we can only use when we know what is this ht and then gt, right. So, but here if you substitute boundary condition eta is equals to 1, eta is equals to 1, that means r is equals to capital R. At r is equals to capital R, t is equals to t naught. So, theta is nothing but t minus t naught, so that should be 0. So, theta at 1 comma t should be 0, ht multiplied by exponential of minus capital lambda should be equals to gt divided by capital lambda. So, that in place of gt divided by capital lambda we can write ht multiplied by exponential of minus capital lambda. So, that we write and then take ht common. So, we have ht function of e to the power of minus delta by eta minus e to the power of minus lambda. So, then we have this equation. So, it is better compared to this equation, but still there is a ht. Without this one we cannot use this equation. So, now we have to evaluate this ht. From this interfacial energy balance, what we got? Q naught is equals to minus kg dou t by dou r at r plus is minus rs delta h by r. So, that means dou t by dou r is equals to rs delta h r by kg. This equation we non-dimensionalize. So, this equation same written here. If you non-dimensionalize, then we have dou theta by capital R dou eta is equals to rs delta h r by kg. That capital R of left hand side we bring to the right hand side, and then substitute eta is equals to 1, because we are doing at r is equals to r capital R. So, at r is equals to capital R, eta is equals to 1. So, that is a constant actually. So, that capital gamma we are calling, right. Now, equation 14, this is what we have. We will differentiate this equation also with respect to eta and then substitute eta is equals to 1. So, by differentiating with respect to eta, this is what we have, and then substituting eta is equals to 1, this is what we have. So, that these two equations you can compare and then have an expression for ht. So, ht would be capital gamma by capital lambda e to the power of minus capital lambda, right. This is what we have. This now you can substitute in equation number 15, so that you have the temperature profile. This part is nothing but your ht. So, we came over this ht as well. So, next step what we do, e to the power of capital lambda we bring in inside the parenthesis, so that we have this one, right. Now, we wanted to measure the temperature at infinity location. Actually, theta is nothing but T minus T naught. So, minus theta would be T naught minus T, and then if you are evaluating this theta at infinity, that T should be T infinity. So, T naught minus T infinity would be minus of this one. So, this and then eta is infinity. So, 1 by eta is 0. So, this part is there here. So, T naught minus T infinity is nothing but this all expression. From here we can get final T naught expression. T naught is nothing but T infinity plus minus this expression. But capital lambda is very less than 1, that is particle is very small in general, then e to the power of capital lambda minus 1 is approximately capital lambda. So, that we can have T minus T infinity is equals to minus simply capital gamma. So, then this is what the expression. So, this is the overall general solution, this is the solution when particle size is very small for the surface temperature. Okay. So, the references for this problem are provided here, but this problem is taken from this reference book. Thank you.